Modern large language models run on autoregressive generation. They predict the next token in a sequence over and over at blistering speeds. But this architecture harbors a severe blind spot: the complete inability to pause, reflect, or evaluate what it just produced. Because this process is purely forward-moving, models execute complex cognitive tasks rapidly, but they do so entirely without native uncertainty monitoring. There is no internal mechanism checking if the sequence it is building actually makes sense. The direct consequence is the generation of high-confidence hallucinations. A model aggressively pursues a brittle logic path, outputting completely false information with absolute mathematical certainty. In human psychology, the solution to this is metacognition, an internal perception action loop where the brain monitors its own cognitive processes and regulates them accordingly. Basic cognition is the act of generating an answer. Metacognitive processing is knowing whether that answer is actually correct before you say it out loud. High task performance on benchmarks does not equal self-awareness. To build systems that actually know what they don't know, engineers have to design and build a distinct metacognitive layer. This diagram maps the blueprint required to bridge the gap between passive text generation and active self-regulation. Notice the central axis. A query comes in, passes through a monitor, goes to the language model, passes through a control node, and results in an output. The monitor node acts as the engine for self-assessment. This is where the system forms judgments about its own uncertainty and tracks its progress against the initial goal. The control node is the mechanism for self-regulation. Based on what the monitor flags, this node adjusts the planning and strategy, reallocating effort before the final output is executed. For true metacognition to exist, these two nodes must form a continuous feedback loop surrounding the central cognitive processing unit. Baseline language models lack this explicit feedback mechanism in their native state. They consist almost entirely of that central cognitive node, stripped of the surrounding regulatory infrastructure. Without this fully connected loop, autonomous AI agents cannot catch their own cascading errors. They will inevitably remain brittle and unsafe for multi-step deployment in the real world. The industry typically evaluates model safety using probability metrics, like expected calibration error, or AROC. Researchers classify these as Tier 1 and Tier 2 metrics. They are dangerous because they heavily conflate a model's raw task capability with actual self-awareness. A model simply good at answering questions will score highly, masking the fact it cannot accurately predict when it is about to fail. To cleanly decouple cognition from metacognition, researchers borrow signal detection theory from cognitive psychology. In this framework, the variable D' represents the model's Type 1 task sensitivity. This is simply its raw ability to get the answer right. We separate that from meta D'. This represents the model's Type 2 metacognitive sensitivity, its ability to discriminate between its own correct and incorrect responses. By dividing meta D' by D', we get the M ratio. This isolates the model's true metacognitive efficiency, independent of baseline task smarts. When we evaluate modern large language models through the M ratio, the empirical findings reveal a massive knowledge confidence gap. Models consistently express absolute certainty on questions that fall entirely outside their internal knowledge boundaries. We also observe a phenomenon called escalating certainty. In long chains of thought, the further a model reasons, the worse its metacognitive sensitivity becomes. The reasoning process itself paradoxically blinds the model to its own errors. This proves that models do not naturally know what they do not know, and simply scaling up the parameter count does not close the gap. Until engineers isolate and measure metacognition accurately via the M ratio, attempting to fix overconfidence with broad structural patches will fail. The earliest attempts to fix this metacognitive loop relied heavily on prompting interventions. Engineers essentially overlay a prompt filter onto the monitor node to force structured System 1 and System 2 thinking. Techniques like the Monitor, Generate, Verify framework instruct the model to explicitly pause. The prompt demands the model generate a draft, review its own logic, and verify the facts against the initial instructions. This artificially forces the model to evaluate its own uncertainty before finalizing an output. But this approach is architecturally brittle. It relies entirely on surface-level alignment. The model is essentially role-playing as a self-aware entity because the prompt told it to, rather than relying on a structural change in processing probability. It also carries a severe model size constraint. When engineers apply metacognitive prompting to sub-9 billion parameter models, the models often hallucinate worse, introducing new errors into their own self-reflections. Prompting is a useful bandage for directing the outputs of massive models, but it is not a native architectural solution for genuine self-regulation. To solve the root problem, researchers moved past superficial prompting and began developing deep post-training interventions that permanently alter the model's weights. One of the most effective methods is reinforcement learning with metacognitive feedback, or RLMF. Instead of just rewarding a model for getting the right answer, RLMF accurately judged its own performance. The training pipeline scales advantage scores based on this feedback. If a model provides a correct answer but expresses unwarranted absolute certainty, the algorithm penalizes the weights. The ultimate outcome of RLMF is faithful calibration. The confidence the model expresses in its text perfectly matches the actual mathematical uncertainty of its internal processing. The most advanced interventions, considered level 3, utilize agentic architectures. Instead of relying on a single neural network, they physically break the loop apart, separating the monitor and control nodes into distinct parallel agent blocks that communicate with each other. This strategy completely decouples execution-level reasoning from task-level monitoring. The agent doing the thinking is no longer the agent grading the work. For instance, engineers will deploy a fast consistency monitor to check raw facts against retrieved documents, paired with a slow experience-driven monitor that accesses memory records to adjust the system's overall retrieval strategy. This physical separation ensures the primary language model cannot override its own doubts with autoregressive momentum. The monitoring agent serves as a hard stop. By physically separating these cognitive nodes, engineers create genuine, structurally robust metacognition that is immune to the forward-moving inertia of standard text generation. This flowchart maps LLM metacognition research. These self-regulatory loops unlock new downstream capabilities. The engineered loop directly drives hallucination reduction and confidence calibration, ensuring the system only asserts what it mathematically knows. It also enables knowledge boundary detection, allowing the model to accurately define its limits and gracefully abstain. The core realization is that metacognition does not automatically emerge simply by scaling up a model's parameter count or feeding it more text. Metacognition is an entirely orthogonal axis of intelligence. It requires explicit, deliberate optimization by engineers at the architectural level. The long-term frontier of this research is continuous, autonomous self-improvement. Zero-shot autonomous improvement is mathematically impossible if a model cannot intrinsically evaluate its own failures and test the validity of its own strategies. By embedding these metacognitive loops, engineers are building systems that can accurately grade their own logic, allowing them to adapt to novel environments and refine their reasoning without human supervision. Autoregression built a powerful cognitive engine. The engineered metacognitive loop finally provides the steering wheel.